yn minus 1 is equal to nebula yn minus 1 minus nebula yn minus 2. And so on and so forth. Nebula 2y4 is equal to nebula y4 minus nebula y3. And nebula 2y3 is equal to nebula y3 minus nebula y2. So this gives us the backward difference, second order backward difference. Let's have a look at it in the tabular form for better understanding. Given the values of x and y, x1, y1, x2, y2, x3, y3, and x4, y4, we had already earlier computed the three backward order differences, first order backward differences, that is nebula y4, nebula y3, and nebula y2. Now we have the onerous task of computing the second order backward difference. So nebula 2 y4 is given by the difference of nebula y4 minus nebula y3. So y4, that is the first order backward difference, nebula y4 minus the first order backward difference, nebula y3. The subtraction of the two would give you the second order backward difference. Similarly, nebula 2y3 can be computed as nebula y3 minus nebula y2. Since there are 4 points, the number of terms in second order backward difference would be 4 minus 2, which is equal to 2, and hence we have got 2 terms in the second order backward difference. Very simple. Let us move ahead to third order backward differences. The differences of the second order backward difference is the third order backward difference. So nebula 2yn minus nebula 2yn minus 1, nebula 2yn minus 1 minus nebula 2yn minus 2, so on and so forth to nebula 2y5 minus nebula 2y4, and nebula 2y4 minus nebula 2y3. These will give us the third order backward differences for a table of n points, and they are denoted by nebula raised to 3 or nebula 3. Therefore, I can say nebula 3yn is equal to nebula 2yn minus nebula 2yn minus 1. Nebula 3yn minus 1 is equal to nebula 2yn minus 1 minus nebula 2yn minus 2. So on and so forth. Nebula 3y5 is equal to nebula 2y5 minus nebula 2y4. And nebula 3y4 is equal to nebula 2y4 minus nebula 2y3. Let us look at it in a tabular form for further understanding. So given the table of 4 points, we already computed the 3 first order backward differences as well as the 2 second order backward differences. Now let us compute the third order backward difference, which is given by the difference of the second order backward differences. So nebula 3y4 is equal to nebula 2y4 minus nebula 2y3. The difference of the previous, that is for third order, the difference of the second order differences. Now since this is a table of 4 points, the number of terms we have for third order forward difference is equal to 4 minus 3 equal to 1, and therefore we will have only one term for the third order forward differences. Third order backward difference. So this is how the table is depicted. Let us have a look at the backward difference table for 4 points. This is how it would look. For 4 points, the last order of backward difference that can be computed is 4 minus 3. 4 minus 3, that is 4 minus 1, that is 3, and as a result of which it is we can compute up to third order forward difference forward differences or third order backward differences, and we have in this table a lower triangularization of the values. So unlike the forward difference table where the values were concentrated at the upper triangle, now we have the values concentrated at the lower triangle. Let's have a look at the backward difference table for 5 points. This is what it looks like. Since we have got 5 points, that is n is equal to 5, the number or the order up to which we can compute the backward differences is n minus 1, that is 5 minus 1, which is equal to 4. And so we can compute up to fourth order backward differences. You can again see in this particular table also, despite that we have got one additional value x5, y5, that is the table of 5 points, we still have the lower triangle saturated, whereas the upper triangle remains empty. So what we say is, when we have a backward difference table constructed, we have the lower triangle saturated, whereas when we compute or we construct the forward difference, we will be having the upper triangle saturated. So this is how the backward difference can be computed. Let us take up an example and construct a backward difference table for better understanding. We will take up the same table that we considered in case of forward difference construction. Let's take 5 points where x given are 9, 10, 11, 12, 13, and the values of y given are 5, 5.4, 6, 6.8, and 7.5. Let us construct the table. First, we shall put in the values that have been given to us. X is equal to 9, y is equal to 5, 10, 5.4, 11, 6 and 12, 6.8, and 13, 7.5. These are the values that have been given to us for x and y. We need to compute the backward difference table to begin with. Okay, one thing that we have got 5 points. So the order of backward differences that we would need to compute up to is n minus 1. N is equal to 5 in this case. So 5 minus 1, 4. So we shall be computing backward differences to the order up to 4. So up to 4th order backward differences can be computed for the given set of values. So first and foremost, let us compute the first order difference, nebula y. Nebula y, we begin from computing at the bottom or at the rear end. So nebula y5 is given by y5 minus y4, which is 7.5, minus 6.8, which is 0.7. Nebula y4 is given by y4 minus y3, which is 6.8 minus 6, which is equal to 0.8. Nebula y3 is given by y3 minus y2, which is 6 minus 5.4, which is equal to 0.6. And nebula y2 is given by y2, which is 5.4, minus y1, which is 5, and the value of nebula y2 is 0.4. Since we have already covered all the values from y1 to y5, this is where we stop computing the first order backward difference. Since there are 5 points, the number of terms in the backward difference for first order backward difference would be 5 minus 1, which is equal to 4, and we have already computed 4 terms for the first order backward difference. Let's move ahead to compute the second order backward difference, which is denoted by nebula 2 y. So nebula 2 y5 can be computed as nebula y5 minus nebula y4. Second order backward difference is computed as a difference of the first order backward difference. So that is nebula y5 minus nebula y4, which is 0.7, minus 0.8, which is equal to minus 0.1, and nebula 2y5 is now minus 0.1. Nebula 2y4 is equal to nebula y4, that is 0.8, minus nebula y3, which is 0.6. So 0.8 minus 0.6 is 0.2, which corresponds to nebula 2y4. And nebula 2y3 can be obtained as nebula y3 minus nebula y2, which is 0.6 minus 0.4, which is equal to 0.2. So nebula 2y2 is equal to 0.2. Again, I repeat, we have a table of 5 points. N is equal to 5. Number of terms in the second order backward difference should be n minus 2. So 5 minus 2, which is equal to 3. And we now have 3 backward order differences already available to us. Let us move ahead and compute the third order backward difference. So third order backward difference is computed as the difference of the second order backward difference. So let us start computing the backward difference from the last point, that is nebula 3 y5 is given by nebula 2 y5 minus nebula 2y4, which is minus 0.1 minus 0.2, which is equal to minus 0.3. So nebula 3y5 is equal to minus 0.3. And nebula 3y4 is computed as nebula 2y4 minus nebula 2y3, which is 0.2 minus 0.2, which is equal to 0. Since we have a table of 5 points, the number of terms for the third order backward difference would be 5 minus 3, which is equal to 2. And so here we have already computed the 2 terms for the third order backward difference. We need to complete the table. We go ahead with the fourth order backward difference, which is denoted by nebula 4y. Nebula 4y5 is computed as the difference of nebula 3y5 minus nebula 3y4. That is nebula 4y is, there's a fourth order backward difference, is computed as the difference of the third order backward differences. And in this case, it is minus 0.3 minus 0, which gives us a value of minus 0.3. Now, since we have a table of 5 points, the number of terms in the fourth order backward difference would be 5 minus 4, which is 1. And as a result, we have one fourth order backward difference in the table. Now, we do not have any more values in order to compute. So what we have here is a backward difference table for a table of 5 points. And again, you can see here that the values are concentrated at the lower triangle with no values at the upper triangle. So this is how we could construct the backward difference table. Let us now move ahead and talk about the observations from the difference table. The higher order differences become smaller in size. So as we move ahead and we compute higher order differences, be it forward differences or backward differences, the value of the differences decreases. That is, it would reduce to a point that at one point, if fx happens to be a polynomial of degree n, then the nth order differences, it could be delta ny for forward difference or nebula ny for backward difference. The nth order difference would be a constant, and the n plus 1th, that is the one after that and higher difference, would be 0. So if you have a polynomial of degree n, the n plus the nth order would be a constant, and the n plus 1th and the higher differences would be equal to 0. Now let us consider a polynomial of degree 2, say x squared plus x plus 41. So we have this table here, just in order to illustrate what I have been saying. We have a table for the values of x. If x takes on 0, the value of y for x squared plus x plus 41 is equal to 41. For x equal to 1, y is 43. For x equal to 2, y is 47. For x equal to 3, y is 53. And for x equal to 4, y is 61. We have a table of 5 points, and hence we can go up to the fourth order forward difference. So let's see the fourth order forward difference. First order forward differences, which is 43 minus 41, which is 2, 47 minus 43, which is 4, 53 minus 47, which is 6, 61 minus 53, which is 8. Second order, you can see, is becoming constant. 4 minus 2 is 2, 6 minus 4 is 2, 8 minus 6 is 2. You go ahead, higher degree terms, because this is a polynomial of degree 2. So up the 2 is, the degree is n, which is 2. So up to nth order, it's becoming a constant value. And n plus 1th, that is for third and fourth degree, it becomes 0. Similarly, if we go ahead and find out Newton's, okay, what we have seen here is the differences which we would be using for Newton's methods for interpolation for equispaced points. Now, we can use forward difference or backward difference in order to use Newton's methods for interpolation. If we use forward differences, then that method of interpolation would be termed as Newton's interpolation method. So that would be using forward difference. And backward difference. But both these differences, forward and backward, can only be used for equispaced points. So if your points are unequispaced, that is the difference between two xi's, corresponding xi's, is not equal, then you cannot use any of these methods. So if the point for which the function value is to be interpolated lies in the upper half of the table, of the difference table, then we use Newton's forward difference interpolation formula. So the basic question is, when do we use forward difference and when do we use backward difference? So when the point in question for which we need to find out the value of y lies in the upper half of the table, forward difference is to be used. And if the point for which the function value is to be interpolated lies in the lower half of the table, then we use Newton's backward difference interpolation formula. And if the point for which the function value is to be interpolated lies anywhere in the middle of the table, you can either use forward or backward difference interpolation formula, depending upon your choice. Let us depict this and understand it better. Say, for example, we've been given this table of x and y, say n points, x1, x2, x3, xn, and corresponding y1, y2, y3, and yn. So if the point or the point, that is x, for which we need to find out the corresponding y, lies in the upper half of the table, then we shall go for Newton's forward difference interpolation method. That is, we would be using forward differences and Newton's method in order to compute the value of y. So when the point in question x lies in the upper half, now you can see that arrow moving in the upper half. Somewhere here I've said 3 points above, 3 points below, and somewhere in between I've put that ellipse to saying that this is the middle value. So if it lies in the upper half, yes, we use forward differences and use Newton's forward difference interpolation formula. And if the point x in question lies in the lower half of the table, that is, it lies in the values at the bottom of the table, then we would make use of backward differences and Newton's backward difference interpolation method. Now, why? If you remember, when we constructed the forward difference table, the values were concentrated towards the upper triangle. So when the point in question for which the y is to be computed lies in the upper half, it is always advisable to use forward differences. The reason is you get more number of values which can be put into the interpolation formula and more accurate results could be obtained. Whereas in case of the point lying at the bottom half or at the lower half of the table, we use backward differences, because if you remember your backward